Check it.
Okay, let's take a look at the do now. So we have a compound interest question here. We say, how much money would you have after 10 years if you deposited $1,000 at 4.5% compounded monthly? So you have to just understand where to put things in this formula, basically, right? So what do we put here in the P? That's the principal, which is the starting amount. So you put your $1,000 there. R is the rate in decimal. So 4.5 is a percentage. It's not a decimal. So to make it a decimal, you have to move the decimal point back 2 spaces or divide by 100. Same thing. So what you get is 0.045 there, right? You take the decimal point, you go back 1, you go back 2. The time, well, 10 years. That would be T, right? And compounded monthly, what do we do for N? We look at N is the number of times per time cycle. So the time cycle here, the time unit here is 1 year. Okay, so we're doing 10 years. So how many times per year? In this case, it's 12. If it's monthly, it's 12. And you have 2 of them. You have an N here, and you also have an N here, right? So those are both 12. So ultimately, your equation is just going to be A equals 1,000, 1 plus the interest rate divided 12 times, because you're getting 1/12 of your interest every month, right? To the power of 12 times the number of years, 10. So there's your setup, and the rest of it is calculator. Now, since I have parentheses and I have a fraction within the parentheses, what I'll do is I'll put the fraction in parentheses just to make sure it doesn't get misinterpreted by the calculator. So it's going to be 0.045 over 12, close parentheses for the fraction, close parentheses for the parentheses, to the power of, and now I have, depending on the calculator, this one actually, it goes up for the power, but most calculators don't. So I would use parentheses in that case, and then multiply the 12 times the 10, or write 120 either way. 12 times 10. So here we go. It should be $1,566.99, which is rounded to the nearest penny. All right, so let's try now a hypothetical situation. Let's say instead of depositing $1,000 as our principal, let's say we only put $1 in an account. Okay, $1. And instead of for 10 years, let's say it's just for 1 year. So P is now $1, and T is now 1 year. The only thing that matters now is the rate and the number of times compounded. Let's see what happens if we, okay. Oh, and one more thing. And let's say the rate that we're using is 100% interest. So basically, it's going to double your money. In 1 year, you'll double your money. It's 100% interest. So after 1 year, your $1 becomes $2, right? That's if you only compound once a year. That's called simple interest, not compounded at all. How much would it be if you started to compound that $1 at 100% interest multiple times per year? So that's what these next questions are. So what I want you to do is this. Try these 3 situations, okay? $1 for 1 year at 100% interest rate, which is 1.00, right, in decimal. So basically your formula is now A equals, your P is a 1, so you don't need the P, 1 plus R over N. Well, R is 1 because it's, 100%. Over N, well, N is going to be different for each one of these, to the power of NT. And we said T was 1 year, so really it's just N. So what I want you to do is use this formula right here and just plug in these N's and see what you get. So plugging in all these numbers, 365, 8670, 525,600 minutes, and 1 billion, into the formula looks like this. So I'll just take the formula itself and move it out of the way here. And let's see what we get. Did anybody get a value for 365? We're going to take this, by the way, to 3 decimal places. 2.714. What was it for 8,670? 2.718. What was it for 525,600? The number of minutes in a year. 2718, no change at all? I guess, okay, let's, you know what, maybe 3 decimal places is not enough. Let's go a little further down. 1, 2 after that. And this one was 27. And for the billion, let's just use all the digits on the calculator. Does anybody have the billion done? Yeah, what did you get? 827? Okay. This number that we're approaching here, do you see a pattern? We're approaching a number. We're getting closer and closer to this number, and it's slowing down. Even though, we're up to a billion here, it's not really changing much, is it? We're getting to a number that is known as E. This number is the basis for a lot of natural sciences and exponential growth. So I'm just showing you how to calculate E. You basically are taking 1 plus 1 over an increasing number, a number that's headed towards infinity, to the power of that same number. And what you get is 2.71828 ... So this number is called E. And E is an irrational number, just like pi. It goes on forever, it never repeats, comes up frequently in mathematics. It's a part of many useful formulas. It got its name from Leonhard Euler, who started using the letter E instead of writing. It's like, somebody decided to use the Greek letter pi for 3.14159.265, whatever. So this is the same idea, using E for 2.78128, whatever it is. Okay. And like I said, the way you get it is simply to take what's called, well, you'll learn about limits in pre-calc next year. You're supposed to take this number and just make it bigger and bigger and bigger. That's what this means. As n approaches infinity, that little arrow means approaches, which is why I ask you not to use arrows for other things. As n gets bigger and bigger, you get closer and closer to the true value of E. Anyway, if you make a logarithm out of this, if you use an E as the base of a logarithm, okay, there's E right there, it becomes what's called a natural log, a natural logarithm. And we abbreviate natural log. You would think it would be NL, right? But I guess because we're already using an L for LOG, they wanted to start it with L, so they went log natural, LN. Now some teachers will just say LN and some teachers will say ln. I was originally in the LN camp, and now over the years I just get lazy, too many syllables, LN, so I say ln. So this is ln x right here. All right, this is log base E of x, this is ln x. And natural logs come up so frequently that, they're worth talking about separately. So we'll do a few exercises here with natural logs just to get the idea of what E does. And then we'll do a couple of applications as to what what natural logs are good for. So the first thing we're going to do is write these two exponentials in logarithmic form. And we know how to write things in logarithmic form. We've been doing it for a while, right? Like for instance, if we had 5 to the x equals, 25, you would take log base of this, so log base this of this equals this, right? Well, this is the exact same situation. It's log base of E of 8 equals this. So the exponential version of this is going to be log base E of 8 equals x. That's the exponential version of this equation. But we have a name for log base E, which is what? Ln, right? Natural log. So you could rewrite this as ln 8 equals x. And there you go. That's a natural log for that equation there. Okay, the second one, we're going to take log base E of x equals 5, right? Going that way. Log base E of this x here has to equal 5. So we just say ln x equals 5. And there's the second one. Okay, so natural logs, they work exactly like any other log. Okay, the base never really mattered with other logarithms. No matter what the base was, the properties of logs were the same. The 4 things that we learned about, the product rule, the quotient rule, the base property of logarithms and the power property, they all work exactly the same way. Everything's exactly the same. But the what do you call it? The base happens to be this thing we call E. All right, let's try solving an equation now. This is ln x equals 1. Now, in this case, you know how with the common log we don't write the 10? Like if I had, for instance, log 10 equals 25, we don't bother writing the 10 here, right? But then if you want to do the circular thing, I guess I don't know why I chose 10 here. Let's make that a different number. Let's make that 15. If you want to do the circular method, you have to go this to the power of this equals this. That's when you suddenly do want to write the base there. Well, here we don't have to write an E because ln means base E, but how are you going to do the circular method unless there's an actual base here, right? So maybe just for the purposes of the circular method, you'll want to put a little E here and say this to the power of this has to equal this. So putting this in exponential form, you get E to the power of 1 equals x. Well, that's it. E to the power of 1 is E, so x equals E. You're done. So now we learned something, actually. Ln of E equals 1. That's a really important thing in calculus. And it actually kind of makes sense because ln means log base E of E. The ln e is log base e of e, and we already know that that's a 1 from the base property, right? I have two logarithms, but I can't combine them because of the 3 that's in front of the ln 10. So just like we did with the other kinds of logarithms, we can take the 3 and move it up here using the power property, right? So now we got ln 10 to the third power minus ln 8. And this now becomes a quotient rule, so we can rewrite this as ln 10 to the third on top, 8 on the bottom, which you can also rewrite as ln 1000 over 8, which I guess if we reduce the lowest terms, and that's it. You can't do anything else after that, so there's your answer there. That's one logarithm. For the next one, we have ln 40 plus 2 ln 1/2 plus ln x. So we'll just take the first two here, and that's a product. Oh, no, actually, we can't combine these because of this 2 here. So the first thing I want to do is take this 2 and put it up here. All right, so that means this becomes ln 40 plus ln 1/2 to the second power. Now, if I write it this way, it looks like 1 squared over 2. So I'll use parentheses to make sure you know the reader knows that I'm squaring the 1/2. Right? And now the square of 1/2 is 1/4. That's 1/4 right there. So now using the product rule on these first two, this is ln 40 times 1/4, which is just ln 10. So now I have ln 10 plus ln x. Using the product rule again, I get ln 10x. Next one, we got 6 ln 8 equals minus 2 ln 4. We're going to put the 6 up here as a power using the power property, and the 2 as well up here using the power property. This now becomes ln 8 to the 6th power minus ln 4 to the 2nd power. This is a quotient, so we get ln whatever 8 to the power of 6 is. That's going to be a very big number. Whatever 4 squared is 16, so that's not a problem. And that's it. All right, how about this last one here? We're going to do the same thing. We're going to take the 2, put it up here, take the 4, put it up here, and this one is already good. We have ln 5 squared plus ln 2 to the 4th plus ln 5y. Once again, two product rules. This is going to be ln, so 25 times 16, whatever that is. Yep, 400. Thank you, Siri. Then we have that, and that's going to be multiplication yet again, so it's going to be ln 2000y. Okay, moving on to solving equations now. Let's solve a couple of equations with this. We know how to solve exponentials when the base is a number. Now we're just going to be doing it with a base of e. Now here's the thing. What you want to do is take the log of both sides. That's what we did recently. We learned that we could take the log of both sides and to solve equations. And the thing is, you want to take a log that will deal with the number you have in front of you. If your base is e, you don't want to take a log log, you want to take a natural log, ln. So the first thing you want to do is get the e by itself. So here's the e. I want to get this part by itself. I'm going to add 5 first. So now I have 4e to the negative 2x equals 8. I'm going to divide both sides by 4. So now I have e to the negative 2x equals 2. And now this is where I'm going to use that property we learned in the last lesson, which is we're allowed to take the log of both sides. All right, and that will let us use the power property to bring this down from the tower, so to speak, right? Take the log of both sides. But which log do you take? Don't take an log base 10, because if you take an log base 10, you're taking the log base 10 of 2.7182. That's not really going to help you much. You get to choose what log you take on both sides, so take the ln, the natural log, on both sides. Watch what happens. This will come down as usual. Now you have negative 2x ln e equals ln 2. What did we say a few minutes ago about ln e being an identity that you have to remember? What is ln e? It's 1. So it, for all intents and purposes, disappears. Look at that. Nice. So we got negative 2x equals ln 2, which ln 2 is a number. You can put it in your calculator. It'll give you a decimal. And we're going to divide by negative 2 to get the x by itself. And our final answer is x equals negative ln 2 over 2, and we're done. Now, if you want to get a decimal approximation for that, put it in your calculator. But, we can keep it as this for an exact answer. Okay, for this next question, we'll get the e by itself. So we'll start by adding 12 to both sides. So you got 3e to the 4x equals 27. All right, next step to get the e by itself, I think I'll just divide both sides by 3, right? That'll do that. And now I'm at e to the 4x equals 9. And now it's time to take the log of both sides. And I have to decide what log do I want to take. All right, well, it's a natural, it's an e for a base, so I'll take a natural log. which means, my calculator can also do natural log, so this is not a problem. If I get a ln, I can do it with the calculator. So ln e to the 4x, all right? Now if you think about it, this base is an e, so you could do this one of two ways. You can realize that the bases are the same here, right? So what's the value going to be? Just 4x, right? That's using the base property. Or you can use the power property, bring the 4x down, and then you have 4x ln e, which is also going to disappear. So either way you do it, you're just getting a 4x. And now 4x equals ln 9. So x equals ln 9 divided by 4. And like I said, if you want a decimal approximation, your calculator can do that. Okay, our job here is to get the x by itself. So this time we have the x is kind of buried inside of a logarithm. And like I was just saying a minute ago, you can't separate this from the logarithm. So you have log 4x, you have 3 times ln 4x, and you want to get to that x. If you remember the power property of logarithms, actually the base property of logarithms, we said that if you had a log of a certain base, let's say 3, and you had a power, an exponential of 3 to some power like 7, that if these matched, you would just get the 7, right? But the converse of that was, if you had an exponential, let's say the base was 7, and you took it to the power of log base 7 of, 5, then your answer was 5, right? So if you had an exponential. Now, here we have a logarithm. We're trying to break this out of the logarithm. So maybe what we can do is change this into exponential form, and that'll allow us to do what we just did. So the first thing I want to do is get the logarithm by itself. I'm going to divide both sides by 3. Now I have ln 4x equals 8, okay? And now this is sort of, being stuck in this logarithm is a lot like being stuck in that tower when you're an exponential. You can't get to that 4x. It's locked into the logarithm. So what we can do is this. The same way we can take the logarithm of both sides of an equation, we can actually make both sides a power of e. Watch this. I'm going to put the e down here as a base for each side of the equation. We can do this. So if this blue thing equals this blue thing, then e to that and e to that have to also be equal. Now here's what's going to happen here. What's the base of this logarithm right here? This is a ln, so it's an e, right? And what did we say? If you had some base to a logarithm of the same base, what happens? They cancel out, right? And then what you do here is, okay, these cancel out and you just get 4x equals e to the 8th power. We can now divide both sides by 4, and we get x equals e to the 8th over 4. And if you want to know what e to the 8th over 4 is, your calculator will tell you, because e like 8, 2.78, whatever. 2.71828 divided, to the 8th power will give you some number, and then divide that by 4. But you know what? We'll leave it this way, so it's an exact answer, not rounded. So that's another thing. That's the, you can take the log of both sides, or you can take the e to the power of each side. That's also available to you. That's something we do a lot in calculus. So, it's a good thing to have in your belt, in your tool belt. All right, last one here is an inequality. And what we're going to do here is use that whole thing. We know that if we have a log of x less than 5, whatever, and this is a base of 3, you're supposed to bring, leave this intact and just bring the base over to the other side. So what you get is x is less than 5 to the 3rd. We're going to do the same thing here. The base here is e. So we're going to bring the e to the other side. So now we have x minus 8 to the 4th power is less than e to the 4th. We have that, okay? And we can take the 4th root of both sides, and that'll just end up with x to the 8th minus e like that. And then we can add an 8 to both sides. You get e plus 8. And there you go. X is less than e plus 8. Now, e is a number, 2 point whatever, so this is x is less than 10 point something, right? And there you go. You can put that on the number line if you like. E plus 8, open circle, shade to the left. Last thing is something called continuously compounded interest. The compound interest formula we've been using requires you to have a number of times per year that you're compounding. That's your n. Well, there is such a thing as compounding every moment of every second of every, whatever. Continuously compounded interest. And that means that there's an infinite number, n is infinity basically, okay? And we saw what happened when n goes to infinity in the beginning of the period. When n goes to infinity and everything else is kind of held at a 1, you get e. So this formula ends up taking on a different connotation. Instead of being, the principal times 1 plus r over n to the nt, it becomes the principal times e to the RT. So this is the continuously compounded interest formula. It's A equals P times E to the power of RT. Now, this is still your principal, this is still your rate, this is still your time, but you notice there's no N because N is now infinity. So we can do an example with this. Angela's grandparents deposited $3,000 into a college savings account paying 4%, compounded continuously. What's the balance in 10 years? So the amount of money that Angela will have will be $3,000. That's your P, okay? Remember, once again, I'll put it on the board here. It's A equals P, E to the RT, okay? Times E to the rate in decimal. Now, 4% would be 0.04. That's the rate in decimal. And we're talking about 10 years, that would be T. And there you go, that's it right there. And that's gonna be 3,000 times E to the power of 0.04 times 10, which is just 0.4. I'll just write 0.4. And what I'm getting is $4,475.47 to the nearest penny. We got a couple of more here, but we're out of time, so I'm just gonna call it at this. We are done. See you at the next video.
Check this.